Hello my students, your physics teacher Hassan Darwish with you. In this video, I'll start with chapter 17 about the atom. And at the end of this chapter, the student should be able to understand the following objectives. Study briefly the historical development of the atom. Discover that every individual atom has discrete energy levels. Third one, write the equation which gives the energy values of the hydrogen atom. Fourth, draw the energy level diagram of the hydrogen atom. 5. Distinguish between the emission and absorption spectrum. Okay? We try to cover these objectives in a series of videos. We start with this one. First, history about the atom, or history of the atom. Thomson's model of the atom. We mean by model means what is the structure of the atom in Thomson's brain. How did Thomson imagine his atom? That's the meaning of model. Okay? So, first, Thomson in 1897 discovered the electron and measured the ratio charge of the electron to its mass, approximately 1.7637 times 10 to the power 11 coulomb per kilogram. And of course, this number is negative, okay? But this is a magnitude, E, an absolute value. Millikan in 1909 measured the charge of the electron as a fundamental charge, 1.6 times 10 to the minus 19 coulomb. Now, if you replace the value of E here, you can get the mass of the electron as 9.1 times 10 to the minus 31 kilogram. You know this number. So, they discovered everything about the electron. Also, the size of an atom, means diameter, is about 10 to the minus 10 meter, which is less than the wavelength of the light. Wavelength of light, which is about 10 to the minus 7 meter. So the size of the atom is smaller than the wavelength of light. That's why you cannot see the atom by your naked eye. Right? Because the size of the atom is smaller than the wavelength used to see this atom by your eye. So you cannot see the atom. Also, an important discovery was almost all the mass of an atom is associated with the positive charge in it. Here, you remember we discovered the electron, which is negative. Clear? And the atom is neutral. So, there is another part of the atom having positive charge. But experimentally, they discovered that almost all the mass is associated with the positive charge. So the question is that how the mass and the charge of the atom are distributed. Okay? So an atom contains positive charge, which we call nucleus now, and negative charge, which is carried by the electron. According to Thomson, how they are distributed within the atom. Now, in Thomson's imagination or Thomson's model, they are distributed like this. According to Thomson, an atom might be what? A sphere. So an atom is a sphere of positive charge with the electrons embedded in it, just like raisins in a pudding. That's why this is called plum pudding model, we call it. Here it is. Here is the atom of, this is the atom of Thomson. I mean Thomson's imagination. The red part represent, which is a sphere, represent the positive charge. The electrons are the small dots, blue dots, which are embedded to the positive, because positive attract negative. And look here, they are at rest. Electrons are static, immobile, cannot move within the atom. Okay? This model is called the plum pudding model. Now let's go to the next model. But you know that this model is not true now in modern physics. Rutherford model. Mr. Rutherford did the following scattering experiment. Here we have a box containing a source of alpha particles. What are the alpha particles? They are helium nucleus. I mean the nucleus of the helium atom. Clear? This is a beam of the alpha particles. Beam of alpha particles means large number of alpha particles, large number of nuclei here, directed toward a gold sheet. This is gold foil or gold sheet. Clear? Look here what happens. Most of the, or more than 90% of this beam crossed the gold sheet. But according to Thomson's model, the atom is what? Positive. Clear? Here. And the small particles called electrons are embedded in this positive. And also here positive alpha. So if we represent on this gold sheet Thomson's model, which represent positive particles, okay? Here is a positive, which are sphere, okay? Now this is positive atom. I magnified it also. This is the next atom. Also this is the atom. Here this is, say, the sheet of Thomson's model. All of these are positive. In your opinion, when positive particles like alpha approaches this positive wall, what will happen to it? Of course, more than 90% must recoil back. But experimentally, Rutherford observed more than 90% crossed the sheet with even no deviation. Only a few particles recoiled back, clear, or deviated at large angle. So how can we interpret this experiment? So the interpretation was, according to Rutherford said the only way to interpret the results of this experiment is to reject Thomson's model. Means to say Thomson's model is not true. And this is right. Why? Because according to Thomson's, all the alpha particles must recoil back and cannot cross the gold sheet. which is a positive wall, and assume that the positive charge is concentrated. Where concentrated the positive charge? In a tiny region at the center of the atom, which is called nucleus. Here it is. This is a positive charge, and the electrons move in uniform circular motion around it. This model is called the planetary model because it looks like the motion of planets around the sun, where the sun is at the nucleus and the planets are the electrons. Clear? Moving almost circular trajectory. This model is much more accepted than Thomson's model. Okay? Now let's go to Bohr's model and see why Bohr also to some extent refused Rutherford model. The condition is that the problem of spectral lines. Now what do you mean by the spectrum of the atom? The spectrum of the atom, or the spectrum, represent the set of colors emitted by the atom. We mean the set of monochromatic waves emitted by an atom, for example, or by an object. Let's look at this spectrum, which is a rainbow. This is called the spectrum of white light. Why? Because it represents the set of colors of white light, and this spectrum is emitted by the sun. Okay? We see here the colors are continuous, or the spectrum is continuous. Clear? Because all colors exist here. Right? So we have continuous range of color. While let's look at the following lamps here. Here we have discharge tube lamps. We have the helium lamp, for example, neon lamp, argon lamp, krypton lamp, xenon lamp. Clear? You see these lamps? They are glowing discharge tube. We call them glowing discharge tube. Now let's look at the spectrum of this, of each lamp. For example, let me choose my arrow. Sorry, here. Here, look at the spectrum. For example, you see, look at the lithium lamp. Only a few colors exist in the form of sharp lines, right? Each color represents here monochromatic wave. Now look at sodium lamp. The sodium lamp is the lamp in the street near your house, which gives yellow color. Look here, it gives only two sharp parallel lines very close to each other. Look at the potassium lamp. Only few colors exist. Do they look like this range of colors? No. Look at the mercury lamp. You see? So, the spectrum of glowing lamp means monoatomic gas is not a continuous spectrum, not like the rainbow. That's why it is called discrete spectrum or discontinuous spectrum. Clear? Why is this? We want to explain this. So Mr. Bohr will explain this in the next video. That's enough for now. Take care. Bye-bye.